In the last session, we have discussed some important problems based upon algebra, and the topics were taken from the portion based upon equations. And today, this is our second session of the workshop, and here we are going to discuss some important problems based upon geometry section. And here we will try to cover the triangles and circles, and also the implementation and application of the theorems from Euclidean geometry will be most important point to be discussed here. So now we are going to start, and here some problems are given. You can see the first problem is based upon the quadrilateral and circle. The second problem is based upon the concept of the length of chords and radius, and also the area of circle. The third problem is based upon the triangles and circles. The fourth problem is based upon the circle and also the concept of tangents. And the last problem, number 5, is based upon the triangle, tangent lines and circle. Also the cyclic quadrilateral will be involved in this problem. So now here the first problem is let ABCD be a quadrilateral inscribed in a circle with diameter AC, and let E be the foot of perpendicular from D onto AB as shown in the figure below. We have to draw the figure, and thereafter you will be able to see the construction for the better clarification. If AD is equal to DC and the area of quadrilateral ABCD is 24 centimeter square, then find the length of DE. So now to solve this, first of all we have to construct the diagram. As you can see here, there will be a circle like this, and here is the center. And now here AC is the diameter, and here AD is the chord, and connecting D to C, and here we are forming the 4 chords AB, BC, CD and DA, and here we have this also at point E, DE, which is perpendicular, and here E is the foot of perpendicular of D onto AB. And now here we can see that if R is the radius of this circle and also angle CAB is equal to theta, and now connecting DB for angle CAB, then we can write the area of ABCD is equal to area of DAB plus area of DCB. If we use this, then DAB and DCB together will form the area of ABCD. So now this is equal to half of, we are using the sine rule for finding the area, ADAB sine angle DAB, and also plus half CD into CB sine angle BCD. Here this area will be half ADAB sine of this angle, and here this is half of DCCB and sine of this angle. So now this is also here, this is given that the area of the quadrilateral ABCD is 24 centimeter square. So now we can put this value here instead of area of triangle ABCD. This is 24 and equal to half of a square root of 2r into 2r sine 90 degrees minus theta into sine 45 degrees plus theta plus 1 by 2 root 2r into 2r sine theta into sine 135 degrees minus theta is equal to r square into cos theta, because sine 90 minus theta is equal to cos theta, so cos theta into sine theta plus cos theta plus sine theta into sine theta plus cos theta. This is equal to r square sine theta plus cos theta whole square, and this is equal to root 2r sine 45 degrees plus theta whole square, and this is equal to dE square. Now we can say that dE is equal to a square root of 24 is equal to 2 root 6, and this is in centimeter because area is in centimeter. So the value of the length DE is equal to, this is the length DE is equal to 2 root 6 centimeter. Now the second problem is in the circle O, the radius R is equal to 5 centimeter. AB and CD are two parallel chords and AB is equal to 8 centimeter and CD is equal to 6 centimeter. Find the length of the chord AC. This question is from the China mathematical competition and the previous problem was from the Singapore mathematical competition. So these problems are also important when you are trying to clear the mathematical competitions at the various regional, national and international level. And also this is useful for your academic results, because if you are studying in a school and trying to do best in mathematics, then such problems are very useful to boost up your concepts and also the clearance of all basic level of the learning mathematics. And also geometry is very important part, so this is important to solve such problems very seriously. So now in the second problem, in the circle O, the radius R is equal to 5 centimeter. AB and CD are two parallel chords and AB is equal to 8 centimeter. CD is equal to 6 centimeter. Find the length of the chord AC. To solve this, first of all we have to construct the diagram as now you can see there is a circle like this and here AB is the chord and CD is the different chord. And also this is given that AB and CD are parallel. So and the center is O, and now we are just taking the CD which is less than AB, so the same chord here, the same length, and connecting partially and now AC is the another chord now we have the different length of chords here, and also OC is the radius and OA is also the radius, so OC and OA will be same. So one more thing, that here we are using the same length CD here upper to the AB, so the length O to this point and O to this point will be same. So here if we are taking the values as given, like this is 4, this is 3, so this will be a square root of, from Pythagoras theorem, this is a square root of under root 3 square plus 4 square and 16 plus 9, so this is equal to a square root of 25, and the length will be 5 here, so this length will be 5 also, and here this will form the right angle because we are dropping the perpendicular from O to the chord CD, so this length and this length will be equal also. So now if this is 4, so this will be 4 also, and here this is 3 and this is 1, and now if this is 3 and this is 5, so this will be a square root of 5 square minus 3 square is equal to a square root of 16, and that will be equal to 4, so we can write this 4, and also because this length is 3, so this will be 3 also, this length. And now what we can do, we can construct the second diagram as if this is CD and this is AB, and also connecting this from the partial line, and the same length DC here. So now in this diagram, this is diagram A and we are naming this diagram B. So from these two diagrams there are basically 4 possible cases, and now we can see in the first diagram as A, the longer length of AC is given by AC is equal to a square root of 4 minus 3 whole square plus 4 plus 3 whole square, and this is equal to a square root of 50, which is 5 root 2. So this is the longer length of AC, and the shorter length of AC can be written as AC is equal to square root of 4 minus 3 whole square plus 1 square, and this is equal to a square root of 2. And similarly in the diagram B, the longer length of AC, the longer length of AC is given by AC is equal to a square root of 4 plus 3 whole square plus 4 plus 3 whole square, and this is equal to a square root of 49 plus 49 a square root of 2 into 49, it means this is 7 root 2, and the sorted length of AC, the sorted length of AC can be given by a square root of 4 plus 3 whole square plus 1 square, and this is equal to square root of 50, means 5 root 2. So now this is the shorter and the larger length of chords, and now this is the length of chord AC, and we can simply mention the length as root 2, 5 root 2 or 7 root 2, the three possible lengths here. This is root 2, 5 root 2 and 7 root 2. So we have the possible length of AC here. The first, this is root 2, the second and the third. We have basically three possible lengths here. Now in the third problem, the triangle ABC, where AB is less than AC, has a circumcircle S. The perpendicular from A to BC meets S again at P, and the point X lies on the line segment AC, and BX meets S again at Q, so that BX is equal to CX if and only if PQ is diameter of S. Now we have to construct the diagram as given in the problem. So we are constructing a circle and here the chord AB QB AP here this is BC and this is AC and also QA. And now this is the point of intersection X here. So now, as shown in the diagram, we can find the relation between the angles as you can see the problem here. The triangle ABC, where AB is less than AC, so here AB is less than AC, has the circumcircle S. The perpendicular from A to BC, the perpendicular from A to BC here, this is perpendicular A to BC, meets the circle again at point P here. This is the meeting point, and the point X lies on the line segment AC. Line segment AC, the point X lies on the line segment AC, and BX here, AC and BX. This is the meeting point of AC and BX, and this meets again at the circle at the point Q, and we have to show that BX is equal to CX if and only if PQ is a diameter of S. Means we have to prove that PQ must be diameter. So we are just forming the PQ as partial line, and this is the element of proof that PQ must be diameter if BX is equal to CX or BX is equal to CX if and only if PQ is a diameter of this circle. So now to prove this, first of all we have to find the relation between the angles as angle CBP plus angle BCA is equal to angle CAP plus angle BCA, and you can see angle CBP means this angle plus angle BCA, and this angle is equal to angle CAP, this angle plus angle BCA as it is. So we can write angle CBP is equal to angle CAP. From here angle CBP is equal to angle CAP, because ABPC is cyclic quadrilateral, so this angle will be equal to this angle, so we can write angle CBP is equal to angle CAP. And now you can see angle CAP plus angle BCA plus angle BCA is equal to 90 degrees, because this is perpendicular to BC, so the sum of this angle and this angle is equal to 90 degree, so we can write this is equal to 90 degrees. And now angle CBP plus angle QBC is equal to angle CBP QBC, CBP and QBC means this angle and this angle is equal to angle QBP. This is obvious because angle QBP is the sum of this angle and this angle. So we can write this as angle QBP, and hence PQ is a diameter of this circle. So angle QBP is equal to 90 degree. From the theorem we can write this angle is equal to 90 degrees. And now we have angle CBP plus angle QBC is equal to 90 degrees. So this will imply angle BCA is equal to angle QBC, and now we can write BX is equal to CX. So this is the conclusion, and this is possible if and only if PQ is the diameter, because if PQ is diameter then angle QBP will be 90 degree, because we know that the any point on the circle will form the 90 degrees from the end of the 2 points of diameter. So now we can say that BX is equal to CX if and only if the PQ is diameter. So this part is proven. Now this problem number 4 is from the Macau mathematical competition, and this is based upon the circle, and this is given a big circle O of radius R, a circle, the second circle B of radius 2R, and two circles A and A dashed of radius R are tangent pairwise. Find the ratio of small r and capital R, means radius of these two given circles. So now first of all we have to construct the diagram, as this is the circle, and here we have to form another circle, as you can see this must be tangent to this circle, and now this is the center of first circle and this is the center of the circle named B as given in the problem. This is the second circle and this is the first circle. This is the big circle and this is the inner circle which is tangent to this circle here. And also if we are connecting the straight line passing through these two centers, so here two other circles will be formed and that must be tangent to the inner circle, outer circle means big circle, and this straight line. So we can construct the circle likewise. And now we are naming these two circles as A and A dashed. So this is A and this is A dashed, and one more important thing, that if we are just taking the semicircle, like here you can see this part or this part. If we are taking this part, so you can form this semicircle like this, and this is the inner circle, and I am using the colors as used to form these circles in this diagram, so you can easily understand the construction. As in this part, and now we have the point accordingly. You can see we are taking the same point according to the diagram here. So this is B, and this will be O, and this will be A. So you can simply understand, like here we are just using the half part of the circle, and this is like here. So and connecting the point of tangent here at P, and A and B, like this, and A to O like this, and also this is perpendicular to the point M. This is the tangent, so this will be perpendicular. And now we have the overall construction, and here we are starting the solution, because the symmetricity, the center O and B are on the internal common tangent of A and A dashed. So this is A dashed, and this is the internal common tangent of these two circles. So it is sufficient to consider a half of the graph, as here you can see. And now let MO is equal to X, MB is equal to Y, and then MN is equal to simply X plus capital R, and this is equal to Y plus twice of R. And we can simply see that x is equal to y plus twice of r minus r, and here since AO is equal to r minus r and also AB is equal to 3r, then by the Pythagoras theorem we can relate this as simply y square is equal to mb square, and this is equal to ab square minus am square. This is equal to 8r square is the value of y square, and now we can use y as a square root of 8r, and this is like x is equal to 2 plus a square root of 8 into r minus capital R, and same we can find x square is equal to mo square. This is equal to ao square minus am square, simply ao square minus am square, a square minus am square, and this is equal to r minus r, the difference of the radius of big circle and small circle, whole square minus of r square, and this is equal to r square minus 2rr. And now we can use this as like 2 plus root 8r minus of r whole square is equal to r square minus 2rr, and this will give simply 2 plus 2 root 8 r is equal to 2 plus root 8 square into r, and now we can simply use this for the ratio as you can see 2 plus square root of 8 into r minus r whole square is equal to r square minus twice of r into r, and here 2 plus 2 root 8 into r is equal to 2 plus root 8 square into r, and now this capital R and small r will give the ratio as r by r is equal to 2 plus 2 root 8 by 2 plus root 8 whole square, and this is equal to 1 plus 2 root 2 by 2 times root 2 plus 1 whole square, and this is simply equal to here 1 plus 2 root 2 and into root 2 minus 1 plus 2 root 2 into root 2 minus 1 whole square by 2, and this is equal to 4 root 2 minus 5 by 2. So this is the ratio of here r by r so we can write the now to solve this problem, as you can see, we have to form a circle, also some triangles, because the two important points we have to use here. The first is D is symmetric point of B with respect to P, and E is the symmetric point of C with respect to line BP. And also we have to draw a quadrilateral ABCD to prove that this will be cyclic. Now we have a diagram according to the problem given. The first is, this is the circle, and in triangle ABC, AB is greater than AC, and the tangent line at B to the circumcircle intersect the line AC at P, and D is the symmetric point of B with respect to P. So here, first of all, AB is the chord, and also this is ABED. ABED is cyclic. Here AC, this is the point for C, and here the tangent from B, and this meet at P here, and also this is to be connect A to D here, and here C to D, C to D, and we have connected C to P here, and also BC is the chord, and also BD is connected, and here is the point E, and now this point and this point will be connected, and we have to prove that ABED is cyclic. So here we will use this as the dotted line with green pen. This is the part to be proved that this is cyclic quadrilateral. So now here we can start by the alternate segment theorem. We can relate the angles. Angle PBC, this is the angle PBC, means this angle, the angle BAC, this angle, and angle PAB, this is angle PAB, which is equal to angle BAC. Also you can say this is angle BAC and this is angle BAP or PAB. Both the angles are same. So we can write that the angle PBC is equal to angle BAC, angle PBC, angle PBC equal to angle BAC, angle BAC, and this is equal to angle PAB, and therefore the triangles PBC, here the triangle PBC and the triangle PAB both will be similar. So we can write triangle PBC is similar to the triangle here PAB, and now this will give the ratio of the portions as PA by PB is equal to PB by PC, and hence this is to be relate that PA into PC is equal to PB square, and this will be equal to PD square. Because of the similarity of the triangles we can write this, and also you can write that the ratio PA and PD. Here this is PA and this is PD, so this and this PA and PD will be equal to PD by PC, and here the angle APD is shared, we can say, because angle APD is for the triangle PCD and for triangle PAD, and for both the triangles this is the common angle. So we can simply write the triangle APD is similar to the triangle DPC, and the theorem here, side angle side, holds, and hence we can write angle CAD is equal to angle PAD is equal to angle PDC. So this is also very important result. We can see now. On the other hand, here C and E both are symmetric, and this is given in the problem that you can see that D is the symmetric point of B with respect to P, E is the symmetric point of C with respect to the line BP. So here we can use this as C and E are symmetric, in the line BP. So we can say in BP, and this will imply angle PDC is equal to angle PDE, and this will be equal to angle BDE, and also angle PBC is equal to angle DBE, and now angle BAD must be equal to angle PAD plus angle PAB, and this will be equal to same as angle PDC plus angle PBC. This is equal to angle BDE plus angle DBE. Now, concluding all the results, this will be equal to 180 degrees minus angle BED. So finally we can say that angle BAD and plus angle BED is equal to 180 degrees. Angle BAD means this angle, and angle BED this angle. The sum of these two opposite angles is equal to 180 degrees. So ABED is cyclic because also the sum of these two angles will be 180 degrees. So this is the cyclic quadrilateral. So here the important points, the first is the using of alternate segment theorem. The second, the use of